And so this is estimation, likelihood, and model fitting. We've got a sample of observations. We can look at that in sample covariance matrix, and we know our log likelihood function looks like this. And we can drop that last y bar minus u transpose because of it's being maximized at mu hat. So what we really care about is this profile likelihood, particularly this trace of k and s, because of these zeros that can happen in that inverse covariance matrix. So only the elements that pertain to non-zero KUV, which is the inverse covariance matrix, non-zero off-diagonal elements will contribute to the likelihood. So we can actually, for the saturated model, our MLE is equal to that sample covariance matrix for sigma hat, and we can also invert it. So, so hypothesis testing, going into that off-diagonal element being equal to 0, the trace then would be equal to some difference between what's 0 and sigma hat and what's 0 and k hat and what's non-zero, and that's sigma basically. And so we can maximize the value of the log likelihood based on that d, and we can look at the deviance. So basically this is saying we can compare two models based on which ones has the zeros and which ones don't. And that's what this is. That's what the likelihood ratio test is, for testing different models of which one has the zeros, which one doesn't. Is there a significant difference between those two models based on the off-diagonal zeros of that inverse covariance matrix? And so our null hypothesis would be that our null hypothesis is the saturated model. So M1 is the simpler model, and M0 is the saturated model. And our null is that M1 is true, the simpler model is true. And so large values of the likelihood ratio test statistic will tell us that that null, the simpler model, being true, is false. And it's chi-squared, and F is the difference, the degrees of freedom is the difference in the number of parameters of the two models, which is the same as the difference in the number of edges. So it goes back to everything we've learned about when it comes to likelihood ratio tests and differences in the number of parameters, which is kind of nice. You know, that's why I really like this area, because there's a lot of overlap. And so this is comparing two models, and if we were to see the output, it would tell us that the simple model doesn't quite fit because the likelihood ratio test statistic is around 8, which is kind of large. So that's what this is. And that's like, this is a function that would compare the two models. And again, I can email out this code so you can actually see it and play with it if you want. And we can also use a function in R to test a single edge, if it should be deleted or not. And so again, the null is that it's the simpler model, so that the edge should be deleted, and the alternative is the more complicated model, the edge is included, which is a little bit backwards. You might think, oh, if you should delete an edge, you would think that's kind of like the alternative, but in this case, that's not the case. So here, we're testing whether meet 13 should be deleted. We're looking at whether, the conditional independence of lean meet and meet 13 given the rest of the variables. And this p-value is actually 0.19, so it's a large p-value. So that's telling us that we should delete meet 13 because that's the simpler model. And this tests the conditional independence of the first two variables given the rest. So this is like lean meet, meet 13, and then all of the other ones is what that's saying. All right, so concentration matrix and regression. But any questions about that? Does that make sense? It's all about the off-diagonal elements being 0 in that inverse covariance matrix. That's really the main. If you leave this talk, just remember that, and you basically know Gaussian graphical models. So there's a cool connection between that and regression, which is really nice, because that's when you can go into prediction and stuff. We can partition our response, our mean vector, our covariance matrix, and our inverse covariance matrix. And this is, multivariate normal theory. We can find the conditional distribution of one set of variables given the other ones, where you have this mean and this covariance matrix. And you can express these covariance matrices in terms of the inverse covariance matrix. So that's what this is doing, which is nice, because now we're back to our zeros and ones again. And so, or zeros and non-zeros rather. So we have a multiple regression of y1 on all of the other variables. And so that's this. And so we can, so this sigma 1 squared, the variance, can be represented by this element, 1 over k11, which is, well, something, one of these. And then the regression coefficients can be derived as minus k12 over k1d divided by k11. So you would take a column vector of this inverse covariance matrix and divide it by the corresponding diagonal element, which is what that's saying. So you take an off-diagonal column vector and divide it by the corresponding diagonal element. And the idea is, if any of these are zero, then beta should be zero, and if any of these are non-zero, then beta should be non-zero. And so that's how you can do, say, variable selection. You can go from beta, you can go from your regression problem and look at the inverse covariance matrix, and that will help you decide whether you should include some of these betas or not. Using the relationship between regression and a concentration matrix. Sure.
So you don't really have any, you only have one observation essentially with this regression?
Yeah, with this one, yeah. But you can make it as a multivariate normal problem, and you can use like a likelihood where you do the product over every observation and do sums. Yeah, so this is just one observation, but you can make it with multiple observations. Yeah. And if you were to do that, that would change. It wouldn't change this relationship. It would change the likelihood and basically how you would multiply these. This would be a vector now instead of a single element. But this relationship would still be the same because it's that P by P matrix basically. And so these are supposedly the regression coefficients. This is telling us the off-diagonal element, so this is actually this part, and this is the residual, which is this calculation. So this is just directly going from, literally saying an R1 divided by K11 is the residual variance, and in R we're saying like negative K12, that vector divided by K11, and that's going to spit out those regression coefficients. So that's what that is doing. Okay, does that make sense? I mean, that's really, for me, what's very powerful about this method is the connection between regression, connection between partial correlation. So that makes it kind of flexible, and you can go from different types of models in regression and make a graph, really. I mean, that's kind of cool about it. So instead of so for me, like, regression is like, yeah, it's cool, you can see your regression coefficients, whatever. But sometimes I like to see it visually. So you can do that with a graphical model. You can go from your output of regression to like making a graph and seeing it visually, which I like a lot. Just to go into another kind of model selection besides AIC and BIC, there's something called G-Lasso. So if you read about Gaussian graphical models, you're probably going to come across the G-Lasso algorithm, graphical lasso algorithm. It's implemented in the G-Lasso package. It's basically the state of the art. It's what everybody uses in frequentist literature, or that or a variant. There's some other ones, some other different penalties, but this is the main idea. It maximizes the log likelihood for that inverse covariance matrix, which is penalized by an L1 norm. So that's what I mean here. Instead of just working with the log determinant and the trace, we put an L1 penalization on that inverse covariance matrix. And that's it. That's what the graphical lasso algorithm does for us, which is what we want. Because at the end of the day, like I said, with that inverse covariance matrix, we look for the zeros. We want to see where are there no edges. So that means we want a sparse matrix. We want zeros. We want sparsity. So so we assume sparsity, and then by assuming it, we need to do some kind of penalty. And so people use this method also in high-dimensional problems, so like when p is greater than n, because you want to drop down all those variables into something that's simpler, because it's just, you can't even use a sample inverse or sample covariance matrix anymore to estimate your to take the inverse and estimate your inverse covariance matrix anymore, because the dimension's too large. You'll have a singular matrix that way. So you need to do a penalty. So a lot of people use this L1 penalty on that inverse covariance matrix to penalize all of the in order to impose more sparsity on your matrix, because that'll make it, you can solve a problem like that more easily. You can use convex programming methods, which is what this is saying. And rho is your penalty parameter. And the smaller it is, the denser your graph becomes. So that's another good takeaway then. So G lasso and zeros in the inverse covariance matrix. And so you can implement it. This is just calling that function, G lasso. And so this is telling us that, well, I can't remember. Body fat, I think this is saying, is only connected to knee and height, chest, abdomen, hip, and something else I forgot. But basically, this is the new graph, which is still kind of hard to read, but it's not as dense as the last one. It's definitely more pared down. Yeah, so it's a little bit, it's less dense. And sometimes, like I said, that might be what you want. You might want something that's that gives you those core variables to study. And at the end of the day, if you have a high-dimensional problem, the idea is to break it down into something that's smaller. Like, you want to select variables that seem to be most related to each other, because that helps with your prediction models and anything else you're interested in. Does that make sense? Any questions? Because I'm basically done. I was going to talk a little bit about my research. So my research is just like, what if the data is not normal? So I've been talking to you about normal data, Gaussian graphical models. We look at that inverse covariance matrix, and what do you do? The only reason why we have that relationship is because of normality. And normality tells us, like, oh, if you have a zero in your inverse covariance matrix, then the two variables that pertain to that zero are conditionally independent given all of the other variables. Like, that's just straight out of normal theory. But what if the data is not normal? Can we still build a model? So there's something called a non-paranormal graphical model, which is it's an extension of your Gaussian graphical model, where you replace your random variables with some unknown smooth transformation function, and you call that normal, basically. It's normal now. And how you do your estimations and all of that, you try to be smart, but that's basically the idea, And you try to take those normal data that we now call normal, and you estimate your graph. So this group, they used this function here, where this is a sample mean, sample standard deviation, and this, they use a copula, basically. So this is the inverse of a CDF normal distribution. F tilde is a truncated marginal empirical distribution function, and they use this to come up with their transformation functions. Plug in those x's that maybe aren't normal to get something that we call normal now, and estimate the inverse precision matrix using these transform variables. Doing the same thing. Like, after you have your transform variables, now we can use normality relationships that we know and love, and look for those zeros and non-zeros in the inverse covariance matrix. So that's what they do, and they found it to be pretty good. Like, they found actually that it's actually pretty robust to assuming that the data is normal when they do this transformation function, because this is a Gaussian copula relationship, and so that already imposes some normality assumption in there, and we're dealing with continuous data, so we don't have any issues when it comes to that. So you know, it's pretty good. The only thing about it is they've got this truncated distribution function. So my research, so yeah, this is the overall idea. You estimate your transformation functions, and then you have your sparsity problem to get that precision matrix. But my research actually tries to smooth out that transformation function. So theirs is truncated, and we're wondering, like, if we use a smooth transformation function, do we get a little bit of performance gain, perhaps?